Have you ever looked at a map of the solar system, identified the position of Mars or Venus, and wondered why space agencies don't simply point a spacecraft directly at the planet and fire the engines until it arrives? The question seems almost embarrassingly simple. And the fact that real interplanetary missions follow trajectories that curve gracefully through space that seem to arc away from the destination before curving back toward it, that take months or years to complete journeys that a straight line would seem to shorten dramatically, appears to demand an explanation that goes beyond engineering convenience or institutional caution. The answer is not that engineers have not thought of straight-line trajectories. It is that straight-line trajectories to other planets are not just difficult or expensive. For the vast majority of interplanetary missions with any realistic propulsion system, they are physically impossible in any meaningful sense. And understanding why requires confronting the nature of space itself as a dynamic gravitational environment rather than the static backdrop that everyday intuition imagines it to be. The first and most fundamental obstacle to straight-line interplanetary travel is that the planets are not where you think they are when you decide to go to them. Every planet in the solar system is in continuous motion along its orbit around the Sun, moving at speeds that are large enough to completely transform the geometry of the navigation problem. Earth orbits the Sun at approximately 29.8 kilometers per second. Mars orbits at approximately 24.1 kilometers per second. Venus orbits at approximately 35 kilometers per second. These are not slow drifts that can be ignored or compensated for with minor adjustments. They are velocities comparable to or exceeding the velocities of the spacecraft themselves relative to Earth. And they mean that the position of any planet at the moment a spacecraft arrives is completely different from the position of that planet at the moment the spacecraft was launched. A mission to Mars that launches when Mars is at a particular position in its orbit will arrive at Mars somewhere between 6 and 9 months later, by which time Mars will have moved approximately a quarter to a third of the way around its orbit from where it was at launch. If you aim the spacecraft directly at Mars at the moment of launch, you would arrive at the point in space where Mars was at launch. But Mars itself would be hundreds of millions of kilometers away in a completely different direction. This means that any spacecraft traveling to another planet has to aim not at where the planet is, but at where the planet will be when the spacecraft arrives, which requires solving a problem of extraordinary geometric complexity. The arrival time depends on the trajectory. The trajectory depends on the launch velocity and direction. The launch velocity and direction determine where in space the spacecraft will be at any given moment after launch. And the planet's position at any given moment after launch depends on its orbital mechanics, which are completely independent of the spacecraft. Finding the trajectory that makes the spacecraft and the planet arrive at the same point in space at the same time is an orbital mechanics optimization problem that has to account for the gravitational field of the Sun along the entire trajectory. The gravitational influence of all other planets that the spacecraft passes close to, the practical limits of the launch vehicle's capability, and the constraints of the mission's science objectives. The result of solving this problem is almost never a straight line, because the path that makes the spacecraft and the planet coincide in space and time simultaneously is determined by the physics of orbital motion, not by the geometry of a direct connection between 2 points. The second fundamental obstacle to straight-line travel is that a spacecraft is not a car on a highway that can simply be accelerated to high speed, driven in the desired direction, and then brake to a stop at the destination. A spacecraft leaving Earth carries a finite amount of propellant, And every meter per second of velocity change that propulsion provides comes at the cost of consuming some of that propellant. The Tsiolkovsky rocket equation, which governs the relationship between propellant mass and velocity change, imposes brutal mathematical constraints on how much total velocity change any spacecraft can achieve with a given mass ratio of propellant to dry vehicle. A mission that attempts to travel in a straight line to Mars would need to do several things that efficient curved trajectories avoid. It would need to accelerate hard enough to overcome the sun's gravity, pulling the spacecraft back toward Earth and the inner solar system, rather than allowing the sun's gravity to be incorporated naturally into the trajectory. It would need to maintain thrust continuously throughout the journey, rather than coasting along a ballistic arc that requires no propellant. And it would need to decelerate hard enough at Mars to stop the spacecraft relative to Mars, rather than arriving on a trajectory that naturally matches Mars's orbital velocity through the geometry of the transfer orbit. The total propellant requirement for this straight-line approach would exceed what any currently conceivable chemical propulsion system could carry, by margins that are not close to being bridged by any near-term technological advance. The sun's gravity is the central physical reality that makes straight-line travel impossible, and curved trajectories not just preferable, but mandatory for all missions using chemical propulsion. The sun's gravitational field permeates the entire solar system, and any spacecraft traveling through that field is subject to a continuous gravitational acceleration directed toward the sun. At Earth's distance from the sun, this gravitational acceleration is approximately 6 millimeters per second squared, which seems tiny but accumulates significantly over the months of an interplanetary journey. A spacecraft that leaves Earth moving in a straight line toward Mars would be continuously pulled sideways by the sun's gravity relative to that straight line path, deflecting its trajectory in a curve that bends toward the sun. To maintain a truly straight-line trajectory, the spacecraft would have to fire its engines continuously to counteract this deflection, consuming enormous amounts of propellant just to fight the sun's gravity rather than working with it. The genius of the Hohmann transfer and other low-energy trajectory designs is precisely that they work with the sun's gravity rather than against it, using the gravitational field to shape the trajectory naturally so that the spacecraft arrives at the destination planet with minimum propellant expenditure. Working with the sun's gravity rather than against it is the key conceptual shift that separates efficient interplanetary navigation from the intuitive but physically incorrect notion of straight-line travel. When a spacecraft performs the departure burn that places it on a transfer trajectory to another planet, it is not simply aiming at the destination. It is placing itself in an orbit around the sun, whose shape is carefully designed so that the orbit naturally carries the spacecraft to the location in space where the destination planet will be at the time of arrival, with no further propulsion required during the transit. The spacecraft is in a sense falling around the sun along a curved path, just as the planets themselves are falling around the sun along their orbital paths. The difference between the spacecraft's orbit and the planet's orbit is that the spacecraft's orbit is an ellipse that intersects both the starting planet's orbit and the destination planet's orbit, while each planet orbits in its own separate ellipse. The spacecraft coast phase, which is the majority of any interplanetary mission's duration, requires no propellant at all because the spacecraft is simply following its gravitational orbit, surrendering to the physics of the solar system rather than fighting it. The concept of the launch window, which determines on what specific days a spacecraft can be launched to reach a particular destination efficiently, is one of the most concrete consequences of the impossibility of straight-line travel. If travel were possible in a straight line with unlimited propulsion, a spacecraft could be launched at any time and simply adjust its trajectory to compensate for wherever the destination planet happened to be. But because efficient transfer trajectories are curves whose shape is determined by orbital mechanics, and because the geometry of those curves relative to the positions of the departure and destination planets changes continuously as both planets orbit the Sun, there are specific periods when the geometry is favorable for efficient transfers and long periods between those windows when the geometry is unfavorable. For Earth to Mars transfers, favorable launch windows occur approximately every 26 months, which is the synodic period of Mars as seen from Earth. Missing a launch window does not simply mean a slightly less efficient trajectory. It can mean waiting nearly 2 years for the next opportunity, a constraint that has profound implications for mission planning, budget, and the human factors of crewed missions, where the crew would have to wait on Mars for the next return window if the mission timeline is disrupted. The energy required to reach different destinations in the solar system is another consequence of the curved trajectory constraint that reveals how profoundly the physics of orbital mechanics shapes the possibilities of space exploration. The energy needed to send a spacecraft from Earth to a destination is measured in terms of the c3, which is the square of the excess velocity relative to Earth that the spacecraft needs at departure. Low-energy destinations like the Moon and Mars have relatively low C3 requirements that match well with the capabilities of existing launch vehicles. High-energy destinations like Mercury, which requires traveling inward against the Sun's gravity while shedding the large orbital velocity that Earth imparted at launch, or Jupiter and the outer planets, which require large velocity increases to escape the inner solar system, have C3 requirements that stress the limits of even the most capable launch vehicles currently available. The Messenger mission to Mercury, for example, used no fewer than 6 planetary gravity assists over a period of 6.5 years to gradually reduce its velocity relative to Mercury to a level where orbital insertion was achievable. Because a direct transfer trajectory to Mercury with a conventional launch vehicle would require a velocity change at Mercury arrival that no practical propulsion system could provide. The practical implications of the curved trajectory constraint for crewed missions to Mars are among the most discussed and most misunderstood aspects of human space exploration planning. A minimum energy transfer from Earth to Mars takes approximately 7 to 9 months depending on the specific launch window, and the geometry of Mars's orbit relative to Earth's orbit means that after arriving at Mars, the crew would have to wait approximately 18 months on the Martian surface before the geometry becomes favorable for a return transfer to Earth. The total mission duration for a minimum energy round trip to Mars is therefore approximately 2.5 to 3 years, with most of that time spent either in transit or waiting on Mars for the return window. Proposals to shorten the transit time by using higher energy trajectories that depart earlier from a straight-line path or that use more powerful propulsion systems to add more energy to the transfer orbit are technically feasible but require propellant masses or propulsions. Technologies that are not currently available. Nuclear propulsion, which could provide significantly higher exhaust velocities than chemical propulsion, is the most commonly discussed technology for shortening Mars transit times, but it remains in the research and development phase without a clear timeline for operational availability. The asteroid belt, the Lagrange points, and the various small bodies of the solar system are destinations where the geometry of low-energy trajectories becomes particularly complex, and where trajectory designers have developed sophisticated techniques for finding paths that require minimal propellant while achieving the desired science objectives. The concept of the interplanetary superhighway, also called the interplanetary transport network, describes a network of low-energy trajectories through the solar system that take advantage of the gravitational dynamics near the Lagrange points of the Sun-planet and planet-moon systems to provide pathways between destinations that require very little propellant, but correspondingly long transfer times. Spacecraft using these low-energy pathways may take years or decades to travel between destinations that a high-energy direct transfer could reach in months. But for missions where time is less critical than propellant mass, these trajectories offer possibilities that simply do not exist with conventional Hohmann transfers or direct trajectories. What the impossibility of straight-line interplanetary travel ultimately reveals is that the solar system is not a static space through which spacecraft travel as ships cross an ocean, moving from point to point along the shortest path between them. It is a dynamic gravitational environment where every body is in continuous motion, where the shortest path between 2 points in space is almost never the most efficient path between 2 moving objects in gravitationally dominated orbits, and where the most efficient trajectories are those that work with the physics of the gravitational field rather than against it, accepting longer paths and longer travel times in exchange for the propellant efficiency that makes missions possible within the constraints of real launch vehicles and real propulsion systems. The curved trajectories that spacecraft follow through the solar system are not compromises forced by inadequate technology. They are the optimal solutions to the actual physical problem of moving between 2 objects that are both in continuous gravitational motion around a common center. Solutions that become more elegant and more efficient the more deeply the underlying physics is understood. And in the elegant curve of a Hohmann transfer ellipse, in the sweeping arc of a gravity-assist trajectory, in the slowly spiraling path of an ion-propelled spacecraft, lies not the limitation of human capability, but the clearest possible expression of what it means to move intelligently through a universe governed by gravity.